This lecture is going to be over section 25.3. If you look at 25.3 through 25.5, we're going to be discussing magnifiers, microscopes, as well as telescopes. So for section 25.3, the primary thing that we're going to be talking about is a magnifier. So when with a magnifier, the inchworm can be placed closer than the near point. The magnifier creates an enlarged upright virtual image. So in other words, what you're seeing here is when the object is placed at this magnifier's focal point, the image is at infinity. So what you're creating here is something that looks like this. It is enlarged, it is upright, and it is virtual. So that's ultimately what we're going to be looking at here for this particular section. So let's go to it. So the apparent size of an object is determined by the size of its image on the retina. If it's unaided, this size depends on the angle subtended by the object at the eye, called its angular size. So when the inchworm is at the eye's near point, its image on the retina is as large as it can be and still be in focus. So at the near point, the inchworm subtends this particular angle. In other words, it makes an angle with a horizontal line that comes through the center of the eye. So that angle is largest when an object is at the near point. A simple magnifier produces a virtual image at infinity, which acts as a real object subtending a larger angle. So the relationship ends up becoming that the size of the angle that's created with this virtual image divided by the actual subtended angle, that ends up being your magnification factor or your magnifier. And theta prime is going to be equal to y divided by the focal length. So basically, when you're wanting to look at a small object, you bring it close to the eye and make the subtended angle and the retinal angle as large as possible. But your eye can't focus sharply on objects closer than the near point. So the angular size of the object is greatest when it is placed at the near point. So we'll assume the average viewer with a near point of 25 cm from the eye. A converging lens can be used to form a virtual image that is larger and farther from the eye than the object itself, as shown in figure 25.12. Then the object can be moved closer to the eye, and the angular size of the image may be substantially larger than the angular size of the object at 25 cm without the lens. So this is used, and a lens used in this way is going to be called a magnifying glass or simply a magnifier. The virtual image is most comfortable to view when it's placed at infinity, and in the discussion that follows, we'll assume that this is what's being done. So again, you're seeing the magnification, the angular magnification here, which is the new angle made by the virtual image divided by the angle made by the real image. So again, that's angular magnification. So to find this, we first assume that the angles are small enough that each angle in radians is equal to the sine and its tangent. So from this, these two angles are given in radians by this relationship. Combining all of those into this, that's where the angular magnification comes about. In general, objects can be placed even closer to the lens. This image will be upright and virtual so long as S is less than F, but it will no longer be at infinity. So for an arbitrary object distance, we have the following, where your angular magnification is going to be equal to this computation. So it may seem that we can make angular magnification as large as we like by decreasing the focal length, the object distance, or both. But aberrations of a simple double convex lens set an upper limit of about 3 to 4. If these aberrations are corrected, then it may be as great as 20. With greater magnification than is needed, we usually need a compound microscope, which we're going to discuss in the next section.